Okay, this is kind of part 2 of thin film interference and how it really works. And there's all kinds of ways to get the interference patterns that we see here. Different phenomena going on here, but really it's all part of the same phenomena involving different mediums where there's refraction and reflection, and then interference of those waves at certain angles to produce constructive or destructive interference. And so that's the basic principle. We need to understand whether the reflected ray is inverted or erect, because that's going to make a difference in terms of our calculation for how much path difference there needs to be in going through the thin film. All right, so enough talk on that. Let's look at an example of this. Well, let's consider the very common phenomena of light hitting a glass. And, optics usually involves glass, right? And we got light hitting the glass, and when it does, some of the light reflects. And in fact, it's about 4%. And you don't want that because expensive optical instruments will typically have multiple different reflecting regions depending on what's going on in the instrument, many lenses and prisms, that kind of thing. And so the problem is compounded with these reflections. It causes distortions. It causes a lot of basically reductions in the quality of the image, and the amount of energy passing through is reduced. The amount of the reflection at a boundary between two different mediums depends on how much difference there is in the two mediums, namely the value of the index of refraction. If the difference is bigger, the reflection is bigger. So that's something to keep in mind. Well, a lens then is often coated. You might have heard of that. Coat the lens. And if you coat it with an index of refraction somewhere between the two indices of refraction of the medium, like air to glass, okay? Coat it with something somewhere in the middle. Then each surface reflects about the same amount of light energy. Now that's good because it can be set up to actually eliminate or partially eliminate the amount of reflection. We'll see how that works. So here is an example of your camera, your expensive camera. Now I guess probably all you have anymore is your wonderful smartphone camera because they're so good, but historically cameras with good optics would be given a coating of magnesium fluoride, and here's a little vial of magnesium fluoride crystals used a lot in optics. The index of refraction is about 1.38, and it can be used to eliminate 550 nanometer light, which is the center of the visible spectrum, so it does it less for the wavelengths above and below that in the visible spectrum. But your eyes that's right in the middle where your eyes are most sensitive also. So that's a good wavelength to design it for. Now, the index of refraction of glass is 1.5. So yeah, this is more weighted toward the 1.5 than 1.0 for the air, but you can't just pick and choose exactly what you want. There's other considerations. Anyways, how thick should the coating be to do the job? So here's where we get to the particulars of how to solve a problem with index of thin films. So you put the thin film coating on. It has index of refraction N, and its thickness is T. That's what that is. T is the thickness. Now, a beam of light hits, some reflects, and some is transmitted through, and all this is what you want. You want the light transmitted through. That's what you really want. But you can't help but have some reflection here, and you can't help but have some reflection here as well. And so what you want is for ray 1 and 2 basically to cancel. You want those canceling so you don't see the reflected light. Wouldn't that be wonderful? Light is reflected, but with this coating you can get it to destructively interfere. And so based on what I just said, we should be able to logically conclude what this path difference needs to be. If you want destructive interference, then what's the difference in the path length? Did you write it down? All right, you got it in your head? Is it going to be a whole wavelength or half a wavelength? Well, whole wavelength means constructive interference. So you want a half a wavelength for destructive. So how much further does ray number 2 have to travel? How much farther does this travel? Well, the entire path is twice the thickness, there and back. And so twice the thickness, we want that to be a half a wavelength. There it is. So 2 times the thickness is a half of wavelength. Now, okay, pause a second. Lambda sub n. Lambda, the wavelength in the material with index of refraction n. You know, when light from air, having a certain wavelength, hits a slower medium, the light slows down and it bunches the wavelength up. The wavelength gets smaller. In fact, it's shortened by a factor corresponding to the index of refraction. We've actually covered that before, but what it turns out simply is that the wavelength in the coating itself with index of refraction n is just the wavelength in a vacuum or air, practically speaking, divided by n. So it's shortened by a factor equal to the index of refraction. Okay, hopefully that makes sense. Now we can finish up this problem. We have to consider, though, what the nature of the reflections are. Here's a reflection. It's going into a higher index, so it's inverted. The one that goes through gets reflected, and it too is inverted. So you got an inversion here and an inversion here, just like in the example we did in part 1. And so those basically cancel each other. So reflections at slower boundaries are inverted, each having a phase change of 180 or a half a wavelength. 180 degree phase change is a half a wavelength. In this particular example, it happens at both boundaries, so you don't have to worry about it. But it's really important to keep that in mind, that the bounce happens and it either reflects right side up or upside down. So the thickness then is, we're going to solve for t. I'm going to solve for t and bring this 2 down here, and we have lambda n over 4. However, lambda n is lambda over n, so instead of just lambda over 4, it's lambda n over 4, but lambda n is lambda over n, right? So you put the 4n. In other words, this is using both these at the same time. So there's the thickness. So that's 550 nanometers, the wavelength, over 4 times the index. And the index is 1.38, gives us 99.6 nanometers is just the right thickness to produce cancellation of the light, the reflected light, at 550 nanometers. So with this lens coating example, we had destructive thin film interference, and that was designed for it. We wanted to eliminate the 550 nanometers. That's what it was designed for. How about the other wavelengths? Well, they'll be partially reflected, because there's not full cancellation. Now, red and violet, being the furthest away from 550, will be reflected the most. And when those 2 extremes of the visible spectrum are combined, we get purple, which is kind of interesting because you will often see when you look at the coating of a lens, you might see what looks like purple. And that's because that is actually the wavelength that most constructively interferes as a result of the reflections, because it's the combination of red and violet. That makes sense? But in any case, we wanted to minimize the reflection, and it was quite successful because it went from maybe 4% to about 1%. And that's not a bad reduction in the amount of reflection. Now, to finish this off, let me do one more example of a soap bubble. Beautiful soap bubble. wavelength of green that is going to be what we view in this example. We've got, we see the green light, okay, from the soap bubble. And we want to know what the minimum thickness of that bubble is. So really, what this graphic is showing here that I'm trying to construct, this is the air, this blue part is the air inside the film. I mean, it's just, a bubble is just a thin film, highly exaggerated thickness here. But we're going to actually figure out what this thickness is. And it's not a centimeter or whatever that looks like, obviously. Okay, so the bubble is floating around and we have air here. We have the soap itself, okay, and then the film with an index of refraction, say 1.35, based on the constituents of the soap. And then we have air again of 1. All right, that's a different situation than we just had with the glass lens coating. So let's consider the first reflection. There's a reflection. And was there a phase change? Yes, there was a phase change. 1/2 a wavelength. It was erect, it went to inverted. Now the second reflection, most of it transmits through, but at the next interface is reflection again. But note now that it goes from 1.35 to 1. So it's a faster medium, so there's no phase change. No phase change. The index of refraction is less, or a faster medium. Okay, so we had opposite things happening there. It's no problem if you just keep in mind that that's super duper important and just consider the total amount of path difference you need now to effect the amount of phase change you really need. Okay, so here's the second ray coming through. We want constructive interference for green, right? In other words, if you see the green, it must mean that the green light is constructively interfering. If it wasn't, you wouldn't see it. There'd be no energy. But there is. It looks green. You're seeing that wavelength constructively interfering. So the total path difference needed is 1/2 a wavelength. And the reason is because you already had 1/2 a wavelength from this one, the first one, and you don't have any reflection here. So you just need a 1/2 wavelength in addition to this 1/2 wavelength to get a full wavelength. Does that make sense? Good. So then twice the thickness, in other words, there and back, has got to be a 1/2 a wavelength. So that when mixed in with this 1/2 wavelength change of the first ray, there's actually a full wavelength difference between these two. So 2t, twice the thickness, is a 1/2 a wavelength. In the medium, lambda sub n, right? So the thickness is lambda n over 4, but lambda n is lambda over n. So lambda over 4n. Now we can plug in the numbers. There's the numbers. And there's the result. All right. Now, when you watch a soap bubble in reality, you don't just see a green soap bubble, do you? It's more complicated than that. It's more awesome than that. The spectrum of colors is generally clear, and the reason why is because gravity, as this thing is floating, gravity tends to cause the filmy material to sag, so it gets thicker on the bottom than on top. So it thins out as you go from bottom to top, or gets thicker from top to bottom. So you have a gradients of different thicknesses, so you see all the colors, which can be quite beautiful indeed. Here's a nice image of a soap bubble where the colors of the spectrum are clearly seen. And here is yet one more beautiful image of a soap bubble taken by this guy here. So he did a great job showing all the complex detail as a result of nature's solution to the thickness at various places with gravity and wind currents and other little factors. But that shows it really, really clearly. And I just want to point out that this lesson was really important, essential for thin film interference to understand qualitatively and quantitatively how to handle the different kind of situations. So if it was confusing, it might be a benefit to watch it again to make sure you understand. And then, of course, practice with the problems. And hopefully, you will be able to say, wow, I understand it. So now it's easy to understand. See you in the next lesson.